Hello everyone, in this video we'll talk about an AMC 10 problem. So the problem is 2021 AMC 10B number 18. It says a fair six-sided die is repeatedly rolled until an odd number appears. What is the probability that every even number appears at least once before the first occurrence of an odd number? So, it's asking what's the probability that, we'll see every even number before first odd number as an example. So I'm going to present the solution that I found first. It's not necessarily the easiest or cleanest or most elegant or most slick solution, but it's the solution I thought was most straightforward for me to think of. So we're going to do casework on number of distinct evens. Let me type this out. Casework on number of distinct even numbers before the first odd number. So let's see what I mean by this. So we could have 0 distinct evens before the first odd. So that just means, so this is number distinct evens before first odd. So this just means we have an odd number to start with and no evens before it. So that happens with probably 1/2. We could have exactly 1 distinct even before the first odd. So this would be something like, oh, we have some sequence of 2s. And then the first odd number. So there's 3 choose 2 ways to pick, or 3 choose 1 ways to pick which one of the 3 even numbers that could occur on a dice, that we have a long string of before the first odd. And then now we need to do casework on the number of occurrences of that even. So if it's just 1, 2, and then an odd, then this happens with probably 1/6. And then I'll multiply by the probability of an odd at the end. If it has 2 2s before the first odd, then it happens with probably 1/6 times 1/6 or 1/6 squared. If we have 3 2s and so on, it will just be 1/6 cubed and so on. So we get this infinite geometric sequence. So this just evaluates to 1/5. You can see it with a variety of different ways. I guess, if we want to find what some infinite geometric sequence equals, it can be an arithmetical geometric sequence or a hypergeometric sequence. The standard way is just to multiply it by the common ratio. So 1/6 becomes 1/36 and so on. 1/6 squared becomes 1/6 cubed. And then you subtract these 2 lines. So let's just box this off and you'll get 5/6 of the sum equals 1/6. So the sum here is 1/5. Okay, so for case 1, we have 3 choose 1 times 1/5 times the probability of the odd at the end, which is half. Now let's say we have 2 distinct evens. So this could be like a sequence of 2s and 4s. Could be a sequence of 2s and 6s. Could be 4s and 6s. So could be any one of those 3. So there's 3 choose 2 ways to pick which 2. Let's call it like S sub 2, 4 or something for this particular subcase. And similarly for the others. So there's 3 choose 2 ways to choose which 2 even numbers could appear before the first odd. And now it's the same reasoning. There's a 2/6 chance it's either 2 or 4. A 2/6 times 2/6 chance that it's like 2 occurrences of that 2 or 4 before the first odd and so on. This is just casework on the number of either 2s or 4s or numbers in this set consisting of 2s and 4s that occur before the first odd. And then the first odd has a probability half of appearing. So now, probably what I should have said at the beginning is we're going to do complementary counting. So there's only 4 cases. You could have 0, 1, or 2, or 3. So this is the third case. 3 distinct evens before the first odd. So this probability is just equal to like 1 minus the probability of like case 0 and the other 2 cases. So now we have to think, we need to check, do we just add case 1 and case 2 and case 0? Well, that's what I thought at first, but if you think about it, the way we computed the probability for case 2 is that we have some sequence consisting of only 2s and 4s, for instance. But this sequence, it could have been only 2s, and that's included in the probability of 2, 6 plus 2, 6 squared plus 2, 6 cubed, and so on. It could have also been only 4s before the first odd. So this case where you only have 2s and 4s before the first odd, it could be that you have only 2s before the first odd or only 4s before the first odd. So this case 2, it actually includes case 1. And in fact, here we could have only 4s as well in this subcase and only 6s in this subcase. So we've counted the probability of only 4s before the first odd twice in 2 of these subcases. And the same for 2s and 6s. So this case 2 is actually not really like a case. It includes case 1, like I'll put it in parentheses, case 1, case 2. Case 2 includes case 1 exactly twice. Now, we still want to count case 1 exactly once, so we need to subtract case 1. So this is the probability of case 2 plus case 1 plus, so it should be case 2, which is one or two distinct evens. This should be 1 or 2 distinct evens before the first odd. And then we need to subtract case 1 because it was included in this case twice. So this probability is, let's see, 3. And then the infinite geometric series is 1/3 plus 1/9 and so on. And you can evaluate that just to be 1/2. So case 2 has probability 3/4 of occurring. Case 1 had a probability, let's see, we should compute it now. This is 3/10. This had a probability 3/10 of occurring, and case 0 has a probability of 1/2 occurring. So the complement of the probability we want to count is just case 0 minus case 1 plus case 0. Sorry, this is case 2/1. So that's 15 minus 6 plus 10/20. So that's 19/20. So this is the complement of what we counted. We've counted all the cases where there are 0, 1, or 2 distinct evens before the first odd. So the only remaining probability is just all 3 odds appear before the first even, or all 3 evens appear before the first odd, rather. Yeah, so this is my second video on this channel, so feel free to leave a comment of what you thought of the video and if it was helpful, and if you have any questions or comments, just feel free to write it in the comments below. Thanks for watching.